Hey everyone, I'm Miss Hu, your physics teacher. In this video, we're going to go through the magnetic effects of current. This is a topic in both the SPM and IGCSE Physics syllabus. Now please keep in mind, what we'll be covering in this video is just the general information about all the stuff you need to know in order to answer the questions in your examination. There is of course a lot more to know about this topic, so if you'd like to know more, please feel free to do your own research or watch my other educational videos. In the meantime, let's get started. In this lesson, we'll be going through the magnetic effects of current in a wire as well as how to determine the direction of magnetic fields around a wire, the magnetic effects of current in a solenoid as well as how to determine the polarity of a solenoid, the factors affecting the strength of an electromagnet, and the applications of electromagnets. So, first things first, the magnetic effects around a single wire. I hope you have managed to observe this activity in your school lab. I have not included the video in here because I'd like to focus on the theoretical aspect so that you will know how to answer the questions in your paper. Now let's look at the diagram on the left first. So over here, we have a complete circuit and we've got the wire that we put through a piece of cardboard. So what we'll do is we'll scatter iron filings around the wire to see what happens. Now, if this circuit was complete and there's current flowing through, you'll find the iron filings, which I will color in yellow over here for a little bit of clarity and to be able to differentiate the different colors here. So let's say these are the iron filings. You'll find that the iron filings will kind of form circular shapes around this wire. Now, what does this all mean? Why we use iron filings is because if you recall what you've learned about magnetism, iron is a magnetic material, which means that it is attracted to magnetic fields. So the formation of iron filings into patterns prove that there are magnetic fields around this wire. If you switch off the current, or this is an incomplete circuit and there's no current flow, and then you try to, let's say you shake this and try to scatter the iron filings again to see if they will form any pattern, you'll find that nope, there's no pattern formed. But the moment you switch off the current, then the iron filings here would start to form again the circular shapes, proving that there is magnetic fields around this wire and the pattern of these fields are circular. If you're wondering, are you sure this is how we prove it? Now let's recall what we have learned about magnets. So just taking a quick look at this picture here. So this is a permanent magnet, a bar magnet. And these black color bits here are actually iron filings. And as you can see, the iron filings form shapes. And if you recall what you learned about magnets, these are the shapes of the magnetic fields that are formed around a permanent magnet. So the iron filings can show the shape of the magnetic fields. And that's exactly what is being shown over here. So again, iron filings prove the existence of magnetic fields around a current that's flowing through a wire. And the shape of these fields are circular. Now, if you also recall what you've learned about magnetic fields around a permanent magnet, there's also directions. Let's say, I'm just going to color this. Let's say this is north and this is south. And if you place a compass within a magnetic field, you'll find that the compass will show directions. Let's say in this case, okay, it's not very clear, so I'm going to use this color. Okay, the magnetic fields seem to all flow in a particular direction, and they always flow from north to south on the outside, and on the inside, okay, let's use another color. Okay, they're flowing from south to north. So on the outside, north to south, and inside the bar magnet is south to north. So this tells us that the magnetic fields also have directions. If we try to observe the directions of the magnetic fields around the wire, we can do this with a plotting compass. So this is a picture of a plotting compass. It's a really small compass that we use in the lab just to observe the directions of the magnetic field. And what you'll find is that the compass all also seem to flow in a particular direction, a circular direction. So say, for example, we have the compass, which I'll draw in green over here, and we place them around the wire, you'll see that the arrows all go in one circular direction. So how do we quickly determine the direction of the magnetic field? So this is where we can use the right hand grip rule. So this rule is used to quickly determine the direction of the magnetic fields around a single wire where current is flowing through. Now, how do we use this? So have your right hand in a fist with a thumb up. So give me the best sign. Right hand this way. Your thumb represents the current direction, and your fingers represent the direction of the magnetic field. So follow this. I'm just going to blow up a little bit more. Okay, so I'm going to match the diagram first, all right? So this is your thumb representing the current, and of course, your fingers represent the magnetic field. Okay, it's difficult for me to match the diagram because we're looking at this in mirror image. So I'm going to use my left hand then. Your current, this is a magnetic field. So how you use this is, look at the circuit. This is the dry cell, and determine the direction of the current. So current, of course, flows from positive to negative, this way. Don't bother about what's going on outside the circuit. We're going to focus on the area where we want to observe the magnetic fields, which is where we've scattered the iron filings. So have your thumb follow the current direction, so it's pointing up, and then observe the fingers. So imagine your fingers have little arrows there, so you can see that the circular direction is this way, and from your point of view, it is anti-clockwise. So that's why the magnetic field here is going anti-clockwise. So this is, of course, in 3D. Sometimes you will come across diagrams that present the diagram in 2D. How is it like in 2D? That means you imagine that if you place your eyeball here, let's color your eyeball, okay, black. Let's have the eyeball here. So the floating eyeball is here. I like to call it the floating eyeball because imagine eyeballs there, right? So floating eyeball, looking at it from this direction. So you can see that the current is flowing towards your view. So it's as if you have the paper in 2D form and you're looking at it, the paper is here, so the current seems to be flowing towards you. So from your point of view, that means paper, the current's flowing towards you. It's coming out of the paper. How we represent this in 2D, let's look at it over here. So let's say this gray color part represents the wire, and these circles are the magnetic fields. Now, we're not going to label out and in. That's kind of strange. So usually there are symbols to represent the current direction. So if the current is flowing out of the paper towards you, towards your point of view, okay, towards you, out of the screen, out of the paper, the symbol is like this. It's a black dot. So remember that when the current is flowing towards you, use your right hand. So have it point towards you. So I'm going to point this towards you. Have your hand follow my hand. So you can see that when current is flowing towards you, the magnetic fields are going anti-clockwise. So drawing the arrows here, you can now represent the magnetic fields as going anti-clockwise. That's how you use the right hand grip rule to determine the direction of the magnetic fields around the current that's flowing in the wire. What about the opposite direction? That means if current was flowing away from you, that means in this case, you have your eyeball on this side, so the current's flowing away from your eye line. So if you're looking at the paper, that means the current's flowing into the paper, away from you. So from your screen, that means it's flowing, where's the camera? Flowing away from you. Flowing into the screen, all right? Flowing away from you, into the paper, away. The symbol for this is a cross. For me, I like to think of it as, okay, X marks the spot, aim for the X. That's why dot is the opposite. So now, using your right hand, have your thumb pointed away from you, and you'll find the magnetic fields are flowing clockwise. So flowing clockwise. This is how we can show the directions of the magnetic fields in 2D. Now, if you're looking at the circles, by the way, and you're wondering, spacing is not regular. What's this? Like incorrect drawing. No, actually, I've drawn the spacing like this on purpose because you also need to understand that the density of the lines represent the strength of the magnetic fields, meaning the closer the lines are together, the stronger the magnetic fields. Obviously, the closer we are to the source of the magnetic field, that means the closer we are to the wire, the stronger the magnetic fields would be. That's why the lines are closer together. The further away we are from the wire, the weaker the magnetic fields. That's why the magnetic field lines are also further away from each other. So that's also another thing to take note. The closer the lines are to the magnetic field, sorry, not the lines, the closer the field is to the wire, the shorter the distance because the magnetic field is stronger. The further away we are, the further apart the magnetic field lines are, the weaker the magnetic strength is. This can also be seen with the magnetic magnetic fields. You can see here they're much closer, and then as we move away, it's kind of getting slowly further apart. Now that we know, okay, there's magnetic fields around a single wire, and this is true for all current carrying wires, by the way. So anything that has currents flowing through it, there are magnetic fields. But typically, you'll find the magnetic fields are not very strong. That's why you find there's no magnetic effects. They're actually there. They're just negligible. They're too weak to even produce an effect. So let's say we want to produce want to observe whether we could produce a stronger effect. So let's say now we take this same wire, we make it into a loop. So now here's a cardboard, we punch 2 holes, place a wire through. So this is one complete circuit. And you can see from this diagram, we have current flowing this way up and then flowing down. Same wire, but because of the way the current flows, they're now flowing in opposite directions. So this is going up and this is going down. So if you imagine that you look at the wire from this perspective, can you see that this is actually kind of the same as what we'll be observing here? Current flowing out and then flowing in. Okay? Well, to you, it'll be flowing out and then flow in. Okay? Current flowing out and then flowing in. So using what you now know about the right hand grip rule, okay, I'm just going to draw the magnetic fields here. So the magnetic fields, if you recall, these would be anti-clockwise. Right? So this is going anti-clockwise or counterclockwise. So they're going this way. Whereas this wire, the current that's flowing away from your eye line, that means into the paper, will be going clockwise. Because the current is flowing in opposite directions, obviously the magnetic fields will also be in opposite directions. But what you'll find is as the magnetic fields meet in the middle, they're flowing in the same direction, which means that the magnetic field gets stronger in the middle. So this in itself means that if you have the same wire and you take this wire into a loop, you can actually create a stronger magnetic field between the 2 wires in the loop. So if we can do that with one loop, what if we make many loops? That means this time we make a coil. So here's the same wire that's been made into a coil. So we've got current flowing here. I want you to imagine, okay, it's connected this way. It's going here, badam, badush, badam, badush, dadam, badut, badap, and going in this way. So if you look at what's happening here, let's zoom in first so that it's you get a better idea of what's going on. Now on the bottom part here, currents all flowing in the same direction, which means the magnetic fields will all be flowing in the same direction. So let's sketch, just roughly what it will look like here first. So going up means that the magnetic field will be going anti-clockwise. So they're going to flow this way, all anti-clockwise. Because the current is flowing in the same direction, the magnetic fields will also be going in the same direction. So you can see here in the middle where they'll meet, they're actually going in opposite directions. So they're going in opposite directions. So what's going to happen is they're going to cancel each other out. But on the outside, along the bottom edge here, can you see they're all flowing in the same direction? So what's going to happen is the magnetic fields are going to melt together. Well, not melt, I'm saying meld. They're going to combine, join together, and form one big loop like this. So one big anti-clockwise loop. Now the same thing is going to happen on the other side where the currents are flowing down. So remember, flowing down, they're all going clockwise. So when they're all going clockwise, just like with the other set, you can see how in the middle here between these points, the magnetic fields are flowing against each other, which means they're going to cancel each other out. But just like with this set, again, see how the magnetic fields are all flowing in the same direction. So this part, they're all going to combine. And they're going to form one big loop that is flowing like this, clockwise. And you can see how in the middle, the magnetic fields from this set and this set, in the middle here, they're flowing in the same direction, which means that in the end, they're all going to point. In this case, for this diagram, the magnetic fields are going to point from right to left. So using a single wire now made into a coil, you can get much stronger magnetic fields. So a coil that has been used to create an electromagnet is typically known as a solenoid. I'm just going to add the word coil here because I realized I only put the word solenoid. So the difference between a solenoid and a coil is this. A coil is basically just a coil. You can make a coil of wire like a spring, or you could just even get normal string and just make it into a coil. But a solenoid is specifically a coil that's used for an electromagnet. So in simplified terms, you can think of it as a solenoid is an electromagnetic coil. So the term solenoid is used specifically for electromagnets. FYI. So now that you have an understanding, okay, this is how the magnetic fields are formed, we don't have to draw this in our exams. This is just to explain to you how the magnetic fields all combine and form around a solenoid. So now that you know, okay, a solenoid has magnetic fields like this, so you'll find that actually the magnetic fields formed around a coil or a solenoid looks very similar to the magnetic fields formed around a permanent magnet. So here are two diagrams to just do a side-by-side comparison. Because the magnetic fields formed around the solenoid are very similar to a permanent magnet, this means that the solenoid, once it has formed magnetic fields, will behave just like a permanent magnet. Because a permanent magnet has polarity, polarity here means it has north pole and south pole. That means that the solenoid will also have north pole and south pole. How to determine this? Very simple. We know, based on the permanent magnets, magnetic fields flow from north to south outside and south to north on the inside. So if you find that, okay, for example, if we just backtrack, okay, it flows outside this way and inside this way, that means that this side is north and this side is south. So solenoids also have north poles and south pole. So as depicted by this diagram, you can see here side by side, here are the similarities. But the thing is, of course, we want to find a simple and easy way to quickly determine the polarity. We can't be like looking at the coil in the lab and okay, here are the magnetic fields, here's the compass and all. So an easy way to use the right-hand grip rule. Now, I know that you're thinking, didn't we just learn about the right-hand grip rule on an earlier slide? This is another way to use the right-hand grip rule. So it's still the same grip. So remember the best sign, okay? Your fist, thumb up, best sign, all right? But we're going to be using this in a slightly different manner. Please raise your right hand to match what you're looking at. So you've got many fingers, right? More fingers than thumbs, I hope. So your fingers will now represent the loops on the coil or the solenoid. So if you look at your hand like, hey, this is just like a coil, right? So this is the solenoid. So your fingers now represent the current direction that's on the solenoid, and where your thumb is, that's where north is. So for example, if you look at this diagram, if this is how the coil is wrapped around this core, and you see, okay, current's flowing this way, have your hand wrap around this way, follows the direction of the current on this coil, your thumb points towards north. That's how we use the right hand grip rule to determine the north pole of the solenoid. That easy. So just a quick reminder about right hand grip rule in case you're like, so many right hand grip rules. Okay, so the right hand grip rule looks exactly the same in both situations, right? But they're used in two different situations. Well, used in two different manners. The first one is used to determine the direction of the magnetic field. How we use this is your thumb represents the current direction, while your fingers represent the direction of the magnetic field. I'm just going to put them as a different color just because. So that's one, to determine the direction of the magnetic field. Same hand grip rule, but used in a different way. This is to determine the polarity of the solenoid. That means we want to determine the north pole. Your fingers now represent the direction of the current on the coil. Your thumb points to where the north should be on the coil, right? So just bear in mind that sometimes the same hand rule looks exactly the same, but they can be used in different situations. Let me say that again. They can be used in different situations to determine different things. So just be aware of when and how to use the rules in different situations. All right. So now that we know how a solenoid can form magnets, the thing is, solenoids are temporary magnets. Let me just backtrack here a little bit. You see, this solenoid is not a permanent magnet. So a permanent magnet is like a magnet bar. That means wherever you carry this bar, whatever you do with it, the magnetism stays. But this solenoid, it only produces the magnetic fields when there's current flowing through it. If you switch off the current, there will be no magnetic fields and therefore no longer a magnet. So a solenoid is an electromagnet because the magnetism is caused by electricity. Permanent magnets, you don't need the electric current, you just have the magnet bar, boom, and that's the magnet. So that's why I've got the definition written here, which you should know. So an electromagnet is a temporary magnet formed when current flows through a coil. So if you switch on the current, then the magnetism is formed. But if you switch off the current, it loses its magnetism. So it's a temporary magnet. The magnetism doesn't stay. And because of this temporary nature, it is actually very, very useful because you can use the electromagnets on demand. Like you want the magnetism, pop, switch on, it's a magnet. But you don't want it anymore, switch off, it loses its magnetism. Now, before we go to applications, we must, of course, understand how we're going to control the magnetic strength of this electromagnet. By the way, if you'd like to make your own simple electromagnet at home, here's one method. You just need to get a dry cell, copper wire that you wrap around an iron nail. And when the circuit is complete, you try and see, can you attract a metal paper clip? So the paper clip, of course, should be iron because you need to be magnetic. And you find that, oh, it can attract, say, a paper clip. Then when you disconnect it, it will no longer be magnetic. It won't be able to attract the paper clip. Okay, let's talk about the factors now. So if you want to remember the factors, it's not difficult. You have to be aware of what is creating that thing in the first place. That means what is creating these magnetic fields? So obviously it's the current, right? So if you want to write out the factors here, let me write it here. Okay, so remember, obviously, if you want the magnetic strength to be stronger, more current, duh, right? So obviously, the magnitude of the current is going to affect the magnetic strength. Now, what else? So if you look at what we've learned so far, so just backtracking. If you have a single wire, yep, you've got the magnetic fields here. But if you have a loop, you can get stronger magnets. And if you put a coil, even stronger. So what this tells us? More loops. So for sure, if you want to make the strength of this electromagnet even greater, then all you need to do is just increase the number of loops on the coil. Please be careful. Don't say more coils. There is only one coil, many loops, or another way to say it, many turns on the coil. So I'm going to put here, because we're talking about factors, number of loops, or you can say turns on the coil. One more factor is the presence of a soft iron core. Now, what we mean by a soft iron core here, the term soft does not refer to, texture, or, it's soft like plasticine. No. Soft in this case refers to the electromagnetic property of iron. Soft iron here refers to the ease of iron gaining and losing magnetism. So you can even have hard iron, but that's not something we say nowadays. So iron that is hard, that means it doesn't gain magnetism easily and it doesn't lose its magnetism easily. They're usually like steel, for example. So they're alloys where it's iron mixed with other impurities like carbon. So that presence of impurities makes it difficult for iron to gain and lose its magnetism easily. But that's also how we can make permanent magnets. So permanent magnets are made when we have this kind of hard magnetic core where we put it into an electromagnet and then it takes a long time to become a magnet. But once it gains its magnetism, very difficult to lose. Soft iron, on the other hand, very easy to gain, very easy to lose. So if you use like pure iron, for example, a pure iron nail, the moment you connect it to a circuit, it straight away gets its magnetism. Ta-da! The moment you switch it off, straight away, pop, loses its magnetism as well. So very easy for it to gain and lose its magnetism. So that's what it means when we say soft. So if you don't have a soft iron core, the coil in itself will still be an electromagnet, but it will be very, very weak. You might not even be able to attract a single paper clip. But if you put a piece of iron inside, the word core here, by the way, refers to the center of the electromagnet. So the iron nail here acts as the core of the electromagnet. So you put a piece of iron as the core, the iron is able to immediately increase the strength of the electromagnet manifold, like even 10 times or more. So straight away you can see, oh, there's an effect. Oh, I can attract an electromagnet. So placing a piece of iron as the soft iron can really strengthen the electromagnet almost, like almost manifold. Very, very high number. So just a note here for you to take note, soft iron. So soft iron is always used. And this is a question you'll come across quite often actually when it comes to electromagnets. Like, why is soft iron or pure iron or iron used? Okay, so how you describe the reason? Soft iron is used in electromagnets because it easily magnetizes and demagnetizes. Sounds very physics-y, right? Yeah, because when you use physics-y words, you sound so much smarter. So the term magnetizes and demagnetizes here just means that it gains its magnetism easily and loses its magnetism easily. That's how we can describe the reason for using soft iron. So applications of electromagnets. So obviously, one obvious use here is you want to lift up Metallic items. So for example, if you're working in a scrap metal junkyard, you cannot expect to be using manual labor to carry all those crazy heavy metals, right? So let's use our brains and use technology. How this works is this part here is made up of the electromagnet. So that means you have inside here the coil that's wrapped around a soft iron core. And when you switch on, I know it's a terrible drawing, okay? This is the coil and this is the iron core that's inside here, okay? It's inside here. Very easy to use. You want to lift up a certain amount of scrap metal. Of course, this has to be ferrous, F-E-R-R-O-U-S. It has to be iron in or magnetic. So you switch on, okay, then it becomes a magnet, zoom, attracts the metal pieces up. Then you want to carry it over, go somewhere to another part of the junkyard, and you want to let go, switch off, and it lets go. Obviously, you need this to be a temporary magnet, because if it's permanent, the metals are going to get stuck there. It's not going to come off. Obviously, cannot, right? So you need the temporary magnetism so that it will be able to become a magnet, and it will lose its magnetism on demand. That's how this works. Here's another example. This is a relay switch. So what we have here on the left side, this is just a diagram to show you the general circuit symbols that's used as a relay switch. So the relay switch is actually only this part. It's made up of number 2 and number 3. So a relay switch is made up of a coil or a solenoid and a switch. So I want you to think of it as this switch is it will be magnetic. So when you complete this circuit, this becomes an electromagnet, then it closes and attracts it. Then when you switch it off, no more current, it opens up again. So what's a relay switch? So from here you can see there are 2 separate circuits. It's like if you're running a relay race, you got the relay race. So you've got someone running, ching, 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 pass the baton to the next runner. Ching, 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 ching. So it's one runner passing on the baton to another runner. Similarly, for switches, in this case, this is one circuit triggering a second circuit. So they're not connected. They're 2 separate circuits. But the purpose of this is for one circuit, when you switch this on, it starts a second circuit. Normally, the second circuit would have a much higher voltage. So why we want to have 2 separate circuits? There are a few reasons depending on the use. So one reason, for example, would be for safety reasons. Like if you want to call a lift and you press the button, what happens is that it will start a relay switch that triggers the motor to move the lift. So why we want it separate is because usually this is a much higher voltage circuit. So for safety reasons, you don't want to have the user switch on the same circuit, because if anything goes wrong with the switch, the high voltage could potentially electrocute the user. So with 2 separate circuits, if anything goes wrong with this circuit, the user will be pressing the button like, why isn't this stupid lift coming? Okay, the motor is spoiled, or the circuit is spoiled, but the user is fine because the user is pressing this circuit. The user will not be touching the high voltage circuit at all. So another use for relay switches would be, you could even use this relay switch to trigger many other circuits. That means, same electromagnet, but a few other circuits you can put around here. So that means from one input circuit, you can trigger a whole different number of output circuits. So you could start off maybe 3, 4, 5 or more circuits at the same time. And then when you switch this off, all of them switch off at the same time. Similar to how a car works. Like if you start the car, then all the things come on, right? Your headlights and your internal lights and the radio and the aircon, they're all different circuits. And then when you switch off the car, all of them switch off at the same time. So that's another use of a relay switch. How does it work though? So here's an example of a diagram. So now there are many different ways which a relay switch can be designed. So this is just a typical or simple example. So here we have the electromagnet connected to the input circuit labeled here as a first circuit. So you can see here, this is a complete circuit with the switch. when you switch this on, current will flow. When current flows through this coil becomes an electromagnet. If you switch this off, it stops being an electromagnet. So now imagine we switch this on, this is now an electromagnet. You have a piece of iron armature here. The iron armature here refers to a moving piece in this mechanism. So you can see here this iron armature is actually one piece like this. It's like an L-shaped piece, and there's a point where it will pivot. So when this becomes an electromagnet, this iron armature will be attracted to the electromagnet, so it's going to move this way. And as it rotates, let's not use blue, let's use another color. Okay, let's use green. As it rotates, this whole thing will also rotate. It's going to push these two together. So it's going to push this second part here. So imagine that they're flexible pieces of metal. And as it pushes this up, this closes, and this is actually another switch. So it closes the switch, and this switch is actually part of another circuit, to the motor circuit, for example. And how does it open again? Well, when you switch this off, this stops becoming an electromagnet. So what happens is now these pieces here are actually springy. So the moment that they're no longer forced to close together, they're going to spring open, and then they'll separate and push the iron armature back into the original position. So that's how the relay switch works. So just to show you, okay, here's a really nice GIF. Okay, I know your generation calls it GIF. My generation calls it GIF. Okay, but anyway, there's an animation here to show you how this works. So when we close this electromagnet will attract this iron armature. You can see how this rotates and pushes these contacts together. This is an actual photo of a relay. So here's the coil. This piece here you can see is the armature, which is connected to the contacts. So as this rotates, this will push this contact to touch this contact, just like over here. And that's how the relay switch works. Another application that you should know about is the loudspeaker. So this is a cut open version. So this is just to show you the cross section of what's inside a loudspeaker. So the loudspeaker is made up of the cone, which is connected to a coil, and the coil is placed inside a circular magnet. So this is the side view, and the magnet here, it looks like this. It's actually circles like this. And okay, so how it looks like. So I've got here this diagram and it's not complete because I want to show you how it looks like. So this part of the magnet, actually, it's a circle inside a donut, and it looks like this. Right? So let's say based on this diagram, okay, this magnet, inside here is the North Pole and outside here is the South Pole. So why? Okay, so we know that magnetic fields would be, of course, from north to south, like this. So that means over here, north to south, they're actually outwards, or like that. Okay, so how do loudspeakers work? So we've got the coil here. The coil is wrapped at the bottom of the cone. And now, what you should remember is that when sound is converted to electrical signals, the sound that's converted to electrical signals, they're changing, okay, from your view, changing in terms of its frequency, right, and amplitude. So as the sound signal changes, the electrical signals will also change in terms of their frequency and amplitude to match the sound. So that means the current that flows through the coil here would increase and decrease in terms of the amplitude and changes frequency as well. So this changes, and the changes are alternating current. So it will flow one way, flow the other way. So it flow one way, it flow the other way, flow one way, flow the other way. Now remember that the solenoid, let's backtrack a little bit. Solenoid has polarity, right? If the current flows one way, this side becomes north. Now remember, if it flows the other way, the other side will become north. So what happens here is that when the current flows one way, one side will be north, and when it flows the other way, the other side will be north. So that means that the polarity changes, and because the magnitude changes, the strength also changes. So this would cause this coil to be changing in terms of its magnetic strength and magnetic polarity. So when you place it inside this kind of magnet, sometimes it will be attracted, sometimes it will be repelled. So it's going to move like this, depending on, of course, the frequency and amplitude. The coil is then going to do this. Boom, boom, boom. And that's how it creates sound waves. Because if you remember what you've learned about sound waves are longitudinal. And longitudinal waves undergo compression and rarefaction. So that's why boom, it's pushing and pulling the air particles. So boom, boom, boom. So that's how it creates the sound waves. And that's how the loudspeaker is able to convert the electrical signals into sound signals. Now, of course, there are a lot more applications of electromagnets. Please do additional reading, or if there's anything you don't understand about how a particular device works, just let me know and I'll do my best to explain in a separate video. In the meantime, look at how all these magnets work in general, and you should be able to take this same understanding and apply them into different devices to understand how the electromagnets work in those mechanisms. So I hope you have found this video educational and helpful. Don't forget to click like and subscribe for more lessons, solutions, and exam strategies from your teacher, Ms. Ho. Happy studying!